Greetings from Istanbul. We are Team SuRover. Our team was established at Sabancı University in 2021 by a group of engineering students united by a shared passion for robotics. Today we proudly present our second generation rover, Light.
Smoked out, no pyro. Keep a mask up on me face, kid, and it's all black. Gotta lie low. Drugs right albino. If you know, then I know. Where did all of that time go? I see pyramids, no Cairo.
We are 9 members from mechatronics, electronics, computer science, and molecular biology, organized into 5 sub-teams. Mechanics team handles the rover's structural design, mobility system, and other mechanical subsystems. Electronics team develops the power distribution, embedded systems, sensor integration, and communication infrastructure. Software team works on autonomy, perception, control, simulation, mission logic, and the operator interfaces. Science team prepares the rover for soil analysis, sample handling, and the scientific tasks. And business development teams take care of sponsorships, communication, and outreach.
Beyond the engineering, SuRover is an active part of wider space and technology ecosystem.
We have represented our team at Saha Expo 2024, IDEF 2025, Takeoff 2025, and Saha 2026. And we will soon take part in International Astronautical Congress 2026 in Antalya. At these events, we have met industry leaders, engineers, and students. We also organize workshops and share our technical knowledge because we believe exploration starts with curiosity and grows through collaboration. We are going to the ERC not only to compete, but to test ourselves, to turn our ideas into working systems, and to turn challenges into achievements. The ERC is where we push our limits and contribute in our own small way to the future of space exploration.
Now, let's hear from our team members how we are preparing for the ERC tasks.
Lightning is engineering to be light, rigid, and unshakable, built for the harshest Mars-like terrain. Its chassis is a carbon fiber monocoque manufactured in-house using sheet metal molds, precision prepreg cutting, and clean room layup and curing, giving us a structure that is both lightweight and highly rigid. The top of the chassis uses aerospace Nomex aramid honeycomb, and carbon fiber tubes joined with aluminum nose keep the design modular and light. Many of the drivetrain's structural components are topologically optimized and CNC machined. The rover runs on 20 BLDC motors with a dual encoder system on both the motor and the gear side. Each wheel has its own independent steering, driven by a low backlash form reducer, a BLDC motor, and an outer encoder for accurate steering control. This year, we redesigned our non-pneumatic tires with a honeycomb pattern, printed in TPU around an aluminum core to give us strong traction and damping on rough terrain. To keep every wheel on the ground over uneven surfaces, the rover uses a differential bar mechanism to push its stability even further.
Power comes from a custom battery pack of 12 Bosch cells, with the cell pressures arranged for optimum performance and a custom harness designed for reliable distribution. A dedicated BMS continuously monitors each cell's voltage and temperature. With this architecture, the system enables our rover to drive continuously for up to 6 hours on a single charge.
A multi-layer fuse architecture provides staged fault isolation across all critical subsystems. The electronics are organized into 2 modular drawers, one for power electronics, converters, and fuses, the other for onboard computers and motor drivers, with active cooling throughout.
Lightning's control and simulation architecture was built to bring together rover's mechanical, electronics, and software systems into one reliable mission platform. At the lowest level, the rover communicates with its motor drivers through a CAN bus architecture. We developed a fully custom embedded drive code for our 4-wheel steering system, tested in MATLAB and validated in 3D physics simulation before running on hardware. Lightning has 3 steering modes: Ackermann, Crab, and Pivot, for long-distance driving, lateral movement, and zero-radius turns in tight spaces.
For autonomy, we follow a seating act cycle, powered by Velocio to construct a modular and scalable architecture. The rover perceives its surroundings, builds a 3-dimensional voxel map, and localizes itself by fusing visual inertial odometry with RTK GPS via an uncentered Kalman filter. Then, it plans obstacle-aware paths toward mission waypoints and executes the driving. Additionally, we implement Avco marker detection and pose estimation for task-specific perception, allowing the rover to identify markers and estimate their coordinates to execute autonomous mission steps. For wireless communication, Lightning employs a redundant Wi-Fi architecture. Two 2.4 GHz links manage core command and control traffic. One acts as the primary channel, while the other serves as a hot backup that assumes control the moment the primary link degrades. Simultaneously, a separate 5 GHz high bandwidth link handles data-intensive operations, such as live camera feeds.
Now, we would like to show what Lightning can do. Here, it drives forward and then backward. It turns right and then left. And it climbs the slope under full control the whole way. Safety is built in from the start. Our emergency stop is wired directly to the battery management system system, so the moment it is pressed, the power is cut and the rover stops immediately.
The drone serves as the aerial partner of our rover. And this year, we are taking it further. We are manufacturing our new drone as a fully custom X8 coaxial quadrotor built on a 7-inch frame. The airframe is in house carbon fiber prepacked with carbon propellers, and the whole drone stays under the 5 kg limit. 8 motors on a 6S pack give it a large margin. Here you can see it take off, move through each axis, and land. Safety is layered through. The operator always has live telemetry and video, and can take manual control at any moment. A launch pad emergency stop disarms all motors instantly. A geofence keeps the drone inside the mission volume, and the drone automatically lands on link loss, low battery, or any flight critical failure, which we demonstrate here by switching off the transmitter.
Our 6 degree of freedom arm is built for precision and rigidity. Every joint pairs a high-performance BLDC motor with a strain wave gear, giving us zero backlash transmission, high torque density, and around 0.01 mm of repeatability. The main structural brace is topology optimized to cut weight without giving up strength, and carbon fiber tubes in the forearm push the stiffness to weight ratio further. Some key end effector components are manufactured by selective laser sintering, which lets us build complex geometries that are light and strong at once. Together, these choices give us a manipulator we trust on demanding planetary tasks.
For high-resolution feedback, every joint carries an encoder on the motor side and an absolute encoder on the gear side. And thanks to sinusoidal commutation, the arm moves smoothly without cogging. All joint communication runs over EtherCAT, giving us deterministic control across the full manipulator. The arm is operated from a pendant with buttons and a dedicated emergency stop for safe operation. A camera on the end effector gives the operator a close view of the task. The arm supports both joint space and task space jogging with the eye-in-hand camera, and we are additionally developing autonomous motion capabilities for repeatable mission execution. With these tools, the arm carries out the full range of ERC operations, setting the main switches and other controls on the maintenance panel, collecting surface samples, retrieving probes, gripping and handling parts, and lifting payloads.
Our science mission is dedicated to quantifying subsurface habitability. To do that, we need to bring back clean, well-documented samples from both the surface and below it, and then weigh, analyze, and characterize them on board. For surface sampling, the arm collects regolith and rock from the chosen site and places them into the onboard sample container. For deep sampling, our drill runs on a precision linear rail with 30 centimeters of vertical travel driven by a BLDC motor, and its depth is tracked live by an encoder on the rail.
For the astrobiological task, we acquire and seal a liquid sample under 100 mm leak-free and measure its pH with a sensitivity of 0.1. Behind every measurement is a plan. We use JMARS to study Hellas Planitia, the Martian region our landing site is drawn from, to choose targets most worth investigating.